in section 4.3, we're dealing with subspaces. In subspaces, you're checking three things. You're checking to make sure that subspace contains a zero vector. You're checking to make sure it's closed under addition, and you're checking to make sure it's closed under multiplication. So those are the three things that you're going to check. Unlike vector spaces, for subspaces, I'm going to ask you to prove that it is a subspace. I might also ask you to prove that it's not a subspace as well, but this one I will ask you to actually prove it is. And when you're proving that something is a subspace, to prove that something is happening, you have to use generic vectors. And what I mean by that is, let's say I was proving something in R2, just, I don't know, something random in R2. If I was proving something in R2, I couldn't say, oh, 1, 2 plus 3, 4, because that only represents a certain specific two specific elements of that. So if I was proving that something was a subspace for R2, then I would need to do it like, I could call it XY AB, because those would be generic, or I could call it X1, X2 plus X3, X4, because those would be generic. So anytime that I ask you to prove that something is a subspace, or for those of you who do plan to do future math and you're proving, you'll do lots of proofs, proving that something is a certain characteristic, always use generic vectors. Okay? So that's what I needed to say about that, starting that part out. All right, on the 4.3 sheet, we showed that the set x1, 0, x3 was a subspace. It talked about the trivial subspaces. So there's two subspaces that everything has. The zero vector is a subspace for every single vector. The zero vector is a subspace for every single vector space, and also the subspace itself. So the zero vector and the subspace itself are the two trivial subspaces. All righty, here we go. So I want you to prove that the set of all 2 by 2 matrices, symmetric is the important part, prove that the set is a subspace. Okay, now we've talked about symmetric before, just briefly in passing. The actual definition of symmetric matrix is that the matrix is equal to its own transpose. So A would be equal to A transpose. On a test, I'm not too bad about giving you obscure definitions that we covered 2 months ago. I'm not too bad about that. So symmetric, if I did give you symmetric on your test, I would say, hey, recall that symmetric means that a matrix is equal to its own transpose. But the one I will give you for sure on your test and your final is singular. So I do expect you to know singular. From here on out, it's a staple in the class. But pretty much anything else, if I gave it to you, I'd give you a hint like that. Now, I'm proving that it is a subspace. So the first thing I want to talk about is the zero vector. 0, 0, 0, 0 is symmetric. That matrix is equal to its own transpose. So the zero vector is in the set. Check. Okay, so that's first. Second, let's do addition. Remember, it is a subspace, so I have to use generic vectors. Okay, this one is symmetric. But that's not a good one because it had zeros in it. If I was using diagonal, my brain was thinking diagonal instead of symmetric. If I asked you diagonal, that could be how you would set up the diagonal one like I just wrote. Okay, so symmetric would look like this. Okay, that's symmetric. Another thing that when I think about symmetric is it's symmetric across the main diagonal. So see, if I flip that matrix over and laid it on its side itself, B would be laying on B. That's how you also know that it's symmetric. But the real reason is if I wrote this as a column, and if I wrote this as a column, I get the same thing. Okay, so that's what a symmetric matrix looks like. So let's add it to another one. Are there any questions with how I knew how those looked? Okay, so I added a symmetric matrix to a symmetric matrix. Let's see what happens. Okay, so that's basic matrix addition. That's how it would look. If I go to look at this one, if I wrote this one as a column, and I wrote this one as a column, it's equal. They're the same. So, yes. Now, I don't want you to say yes and put a check mark. I like check marks personally. That lets me know I successfully did this. But you've got to tie it all up. You just can't say, do what you want with it, right? You have to tell me what happened here. So what happened in this blue statement was this, you could call it the vectors, whatever you want to call it, is closed under addition. Okay, so I want you to have that statement in there. Set would be the proper one. I just need to see closed under addition. That's what I'm looking for. And so that's how that part would look. So that's the second one. So we have the third one. Here we go. The third one is, let's take the same matrix right here. It's good. And let's multiply it by a scalar. Let's call the scalar P. I would call it C, but I already use C, right? So I'm going to call this scalar P. You could call it any letter that you wanted. I picked P. I don't know why. Okay, so that one, if I did go across the main diagonal, PB and PB would fall on each other. If you wrote this as the top row as a column or the second row as a column, it would be symmetric. So this set is closed under scalar multiplication. Okay, now sometimes we want to cut corners, and that's okay. I'm fine with cutting corners sometimes, but don't say that it's closed under multiplication, because it is not closed under multiplication. It's closed under scalar multiplication. So for those of you that like to cut corners, at least write there, right? Where I'll know that you meant for it to be scalar. I prefer you write the whole word. However, don't cut corners and say under multiplication, because it's not true matrix multiplication. Now, that satisfies the three pieces. And this is an appropriate proof for proving that something is a subspace. Do you have any questions with it?
I was thinking the student wants to write this set is closed under scalar multiplication more concisely. The student can say this set is closed under scalar.
Okay.
That would, I would think, mean synonymously with the statement. Scaling a vector would be evaluating the expression of a scalar times a vector.
We just don't use that term in this textbook, so it's not, I'm not saying that it is incorrect, but if we're lining it up exactly like the definition in this textbook, I prefer it to say scalar multiplication, but I'd have to do some research on scaling.
It just probably would be a more ambiguous
Gotcha. I'm not saying I wouldn't take it though. You're gonna make me think. All right, so this is our second one. The next one, or I think it's the second one we've done. Prove that the set of all non-singular matrices is not a subspace. So we can do that one. I like that one a lot, actually. Prove that the set W is not a subspace. Okay, so for the last two of this section, you get to prove that they're not. Those are easier. Okay, we're going to let W be the set of all non-singular matrices. It didn't give you a size here, and so when you're dealing with these and you're proving that something is or isn't, if it doesn't give you a size, just use 2 by 2. Those are going to be the easiest ones to do. So we have to show that all non-singular matrices, we have to prove that this is not a subspace. This is really easy to do. First of all, W has to contain the 0 vector. So for the 0 vector, it looks like this. Now, that's the only 0 vector for matrix C, for a 2 by 2 matrix. That's a 0 vector. What's its determinant? 0. And if the determinant is 0, that means it's what? Singular. But my W is non-singular. So we could automatically say here, the 0 vector is not in the set. Fails. Now I'm going to show you the other way as well, but that's all you have to do is show one. You don't have to show more. As if it fails one, it fails them all, right? So that's how I would do it. Now, I could also ask it the other way. What if it was singular matrices? Well, that passes singular, so we'd have to do something else with it. So I'm going to continue along this thought process to show you something else that might work. Non-singular. Okay, what's this one's determinant? 1. What's this one's determinant? -1. What's this one's determinant? Okay. So you'll say, how did you know to do those? Because now I'm showing it to you, so now it's in your toolbox as well. So if you have something that's singular or something that's non-singular, you can make the same type of argument, whether it's for a vector space or for a subspace. So I added a non-singular matrix to another non-singular matrix, but what I got back was a singular matrix. And so this is not closed under addition. Okay. Now, again, you do not have to put the red and the blue. You just had to do one or the other. This or this. You didn't have to put both. But I wanted to show you another thought process of it. If you try to do this one with scalar multiplication, it's going to pass it. Go ahead.
I was thinking, whenever you were saying that to do proofs, you need to use variables subset, but this is not including proving that a quantity is not a vector space nor a subspace.
Yes.
In which if we're trying to prove it's not a subset or the quantity is not a vector space, in that kind of case we can use constants as improvement.
Okay. See if that helps. So the question was, if we are proving that something is a vector space or a subspace, you have to use the generic examples that would work for every possible one, right? So if the question asks for is, you have to use variables. But the question asks for not, all you have to do is find one itty-bitty loophole, one itty-bitty little pinhole in their argument. And so it can be numbers. You could technically use variables, but variables are sometimes a little bit harder to do. I'm not saying you couldn't. But for a not, all you have to find is basically one counterexample, and it can be a specific. The specific ones are the easiest ones. So the specific examples are fine. So over here, for not, I would say use numbers. And for is, use variables. Good question. Did that answered it? Okay, great. You're welcome.
I had a question. So when you're saying the zero vector, is that when you also talk about non-empty?
Non-empty.
Okay.
That's the non-empty category. Yes, ma'am.
So, number 6 of the homework, it basically asks the same thing, but to prove that it's not a vector space. Do we do it the same way as we do the...
Yes. Proving something is not a vector space is going to be the exact same proof as proving it is not a subspace. That is exactly right. You're asking great questions. Any other questions with it? Okay, going back to this one, normally, of course, I would do a green example, which would be scalar, but this one would pass a scalar test. Okay, it fails the other two, but it would pass a scalar test. So that wouldn't be a good way to prove it's not, because it would pass scalar multiplication. All right, so you've got one more, and the one more looks like this. Perfect. That's right where I was going. You're exactly right. So if I change this to look like this, Joseph made an excellent point. If the problem looked like that, then 0, 0 wouldn't be included. And if 0, 0 is not included, then it fails off the go, right? Nice. Great. Okay, but this one they are included, so we know, and you'll say, okay, so it can equal 0, and that one can equal 0, so 0, 0 is in there. I'm trying to show it's not, so since I'm trying to show it's not, I don't really need to put the 0, 0 in there in this case, because that is, right? So I go to the next one. So the next one would be addition. And we'll think through that for a second. Remember x1 greater than 0 and x2 greater, that means positive. So if I think in my mind, if I add a positive number to a positive number, I'm going to get back a positive number, right? 3 plus 5, that's going to give me positive 8. So it's not going to fail that one either, just off the top of my head. So I think if it was going to fail one, it would fail scalar, okay? So I'm just going to pick my favorite generic example, 1, 2. Okay, because it doesn't give you any, that one's a gray one, and so it does give you a criteria, and the criteria is that the first element has to be more than 0, and the second, or equal to, and the second element has to be greater than or equal to 0. So this is a good element of the set. Remember, scalar, that's something out here. Scalar can be anything. So if I was telling you this is not a subspace, what could I put right here? -1. Okay, so if I multiply this out, I get -1, -2, which is not in the set. And although I know what I meant by this green expression, I haven't summed it all up. So remember, tie it all up in a bow. Prove your point. Get the last line of the argument. That's how you want to think about these. So the last line of the argument is, this is not closed. You can even make it nice and grammatically correct. This set is not closed under scalar multiplication. Okay, and so that's another toolbox to add. So when you think about it with a negative, something being greater than or equal to 0 being the positive or negative, try to use scalar. That's the one that usually fails. So that's another little tool to put in your toolbox. I have another one on my sheet, but I think we already worked that one. Did we work the one on the back page? Okay. So that's what you get. Now then, you have an assignment for me that says work hybrid assignment 7, I think, and that's going to be due on Monday. And again, this video is for fall of 2025. If you're in the future, you may not have a homework. Hopefully you've had a chance to peep at it. Are there any on that set that you would like for me to run through that you had trouble with before you, and it's not due till Monday, so if you hadn't looked at it, no big deal at all. Excellent. All right, we're going to change gears just a little. We're still in the same chapter. Chapter 4, I think we have 2 more sections, maybe. I just copied you some notes. There you go. We'll give you 2 today. There you go. There you go. All right, it changed gear. We're still doing proofs, but the proofs are going to be a little different, and they're going to be more arithmetic, which we like a little better. As long as you can take the determinant, you're going to be good to go. I'm going to do this with it. Okay. Section 4.4 starts talking about linear combinations, spanning sets, and bases. And so that is where we're going with it. So at the top it says write 10, 1, 4 as a linear combination of the vectors here. And so here's basically how it looks. Pretend like, of course I gave you these notes, so they're partly filled in. So I want you to just look at that top paragraph where it says write V as a linear combination of U, V, U2, and U3. And then it gives you this. Now, I gave you this, not this exact problem, but I gave you this problem the other day as a take-home assignment. You all did it. I hadn't entered your grade yet, but I'll do that today. Hopefully I'll get caught up. You've done this problem before. And so when you did this, I want to refresh your memory on how to set it up, because here's how you're going to set up all of this. Section 4.4 and 4.5 will all be set up this exact way. You won't solve it the same way, but it'll be set up the same way. So it's set up like this. This part's very important. So it says V equals A times U1 plus B times U2 plus C times U3. Okay? That's how it's going to set up. You're going to come up with an equation for element 1, 1 all the way across. 10 equals 2A plus 1B minus 2C. 10 equals 2A plus 1B minus 2C. Okay, then we'll go with 1. 1 equals 3A plus 2B plus 2C. 1 equals 3A plus 2B plus 2C. 4 equals 5A plus 4B plus 3C. Okay? A little messy, but that's how it would look. That's how you're going to set these up. Now remember, in this chapter, we're talking about vector spaces. And we say, oh, well, M22 is a vector space, and this is R3. R3 is a vector space, and the set of all polynomials of degree 2 or less, that's a vector space, and they behave the same way. And you're like, how does a ordered triple behave the same way as a 2x2 matrix? This is how. So when I came up with this matrix here, this Gauss-Jordan solve-it-out matrix, right? I set it up by saying element 1, 1 all the way across. Well, that's how you would do your matrices as well. You would set all the element A11s across and set that, so you'd have that equation, and then you'd have the A12 equation, then you'd have the A21 equation, then you'd have the A22 equation, right? And you'd have 4 equations for it. The same thing would be true for polynomials. You would take the coefficients of the x squared term. That would be an equation. The coefficients of the x term, that would be an equation. The constant, that would be an equation. And so that's how they would set up. And that's how these are going to be similar, even though they're not, right? So when we solve this out, and I'm not going to ask you to solve it, but when you solve this out, you would get this statement. V equals 1U1 plus 2U2 minus 3U3. And this is called a linear combination. Okay, and of course the way that we would solve it out is just by using Gauss-Jordan. You wouldn't be looking for x and y and z here. You'd be looking for a and b and c. And so this was your a, and this was your b, and this was your c. Okay, so the main thing of that little lined example was to refresh your memory on what a linear combination is and how to set up these vectors. Okay, so underneath that, you see one with matrices. It says this would also apply to these vectors, and you have those vectors written out. So capital M would equal A times the first matrix, and B times the second matrix, and C times the third matrix, and then you would set that up. Now, when you set up that matrix, you're not going to be able to take the determinant of it because it's not square. You'd still be able to solve it by Gauss-Jordan elimination or Gaussian elimination, but it's not square. It also applies to polynomials. Okay, so the whole purpose is the statement written at the bottom of those notes. It says, look at the top problem. In this problem, we wrote V as a linear combination of U1, U2, and U3. But could any vector be written as a linear combination? In other words, could I put, instead of this one, could I put 7 1/2 square root of 3? Let's not do square root of 3. Bad example. -33? Could that be written as 1? And that is the fundamental question. Could any vector, I pick 1, Natalie picks 1, Will picks 1, Joseph picks 1, could any of our vectors be written as a linear combination? And that's the fundamental question. So what they do, they say, okay, could any V1, V2, V3 be written as a linear combination? Okay, so what they do with that, let me clone this page. Okay. That's how it would look. Now, when I first started teaching linear, which was a long time ago, like some of you might have been in preschool, like in your daycare. So when I did it, I actually tried to work this out because I thought that's how I needed to teach it. And oh my goodness, it was terrible. I'm not saying you can't work it out, but it's variable overload, right? So the question again, remember, the question is, can I write it as an answer? And that goes back to something we've talked about before. Remember, you had this, I made you memorize it like on every test. It says if the determinant is not 0, we know that it has an inverse and it's square, and we said all that. But the one thing that it said was that AX equals B, what? Can be factored, that's true. That is true. That's not what I'm looking for here. However, that's very true. Has a unique solution. So I don't care what the answer is. I'm just asking the fundamental question, can I do it? And so the way that we would tell if we could do it or not is we would take 2, 3, 5, 1, 2, 4, -2, 2, 3, and we would find the determinant of it. If that determinant is not 0, yes, it has a unique solution. I don't know what the solution is, but it has one. For any V1, V2, V3 I could find, it would have one. And so that is where we're going with this particular part. Okay. So the question on the second page says, does this set span R3? Okay. Great. That is what we are going to be doing next time. Okay, so I don't have really time because we're almost out of time, so I don't have time to work it all out. But so what we're going to say is, does the set span R3? What spanning means is, that's the fundamental question on the previous page, can you write V as a linear combination of these vectors? Can any V be written as a linear combination of the vectors? And that is called the span. Okay? Now, they're generic spanning sets. We can go ahead and talk about that, though. They're generic spanning sets. That means that these are the ones, the easiest ones, that span. Okay? So the generic spanning set for R3 would be a 1 in the first position, zeros elsewhere. A 1 in the second position, zeros elsewhere. And a 1 in the third position, zeros elsewhere. Okay, so that's your basic one. And so that's how the spanning sets are going to be for all of your big vector spaces. So M22 would have a spanning set. There's one element. Doesn't matter the order. There's 2 elements. 3 elements, 4 elements. P2. P2 is your set of all your polynomials of x squared or less. So the way that you could think of it would be x squared plus 0x plus 0. Now, we don't want to write it that way, but I want you to see where I'm going with it. Then we could say 0x squared plus 1x plus 0. And we could say 0x squared plus 0x plus 1. So what this spanning set would look like would be x squared, comma, that comma's huge. I'm going to make it a different color in a second. X, comma, and 1. Okay, my students miss this one all the time because they put pluses in it. And I want to explain why it's not pluses one more time. Okay, so I'm asking you for the spanning set. I'm not asking you for an element of the set. X squared plus x plus 1 is an element of the set for sure. But that's not what I'm asking you. I'm asking you, is there a way that I could write every possible, the easiest way to write every possible x squared polynomial out, and this would be the way that we would do it. So you have a 1 here, 0's elsewhere, and that's your first whole polynomial. 1 here, 0's elsewhere. That's your second whole polynomial, which would be 1x, and 1 here, 0's elsewhere. Now, where are we going with this? Let's use the polynomial, for example. All right, Will, I'm going to pick on you today. Sorry. Can you give me any x squared polynomial, just any random polynomial? You said it perfectly. That was on me. Is that what you said? Perfect. Okay, so what a spanning set does is I can take Will's x squared plus 3x plus 2, and I can write it as a combination of those vectors. And those make it easy. It would be something times x squared plus something times x plus something times 1. Okay? So if I was trying to write this out, it would be 1 times x squared plus 3 times x plus 2 times 1. And so that's how we're able to write that as a linear combination of our basic spanning set. And so that's how that comes into play. The other thing I want you to notice about it is that this spanning set right here has 3 elements. That's its dimension. Every spanning set of P2 is going to have 3 elements. This one has 4 elements. So its dimension's 4. We'll definitely talk about that later. And the top one has dimension 3. Now, we just briefly talked about this one. We didn't get very far in it, so we'll talk about this one next time, and we'll finish this little packet out.